All right, everyone, welcome in. We'll give a few minutes for everyone to join us and we'll get started. Just another minute or so. We hope you are having a great day wherever you may be. All right, everyone. Well, I guess I'll do a quick introduction here. Welcome to our webinar. I am Will Azar, Marketing Manager at EPC, and again, welcome to today's edition of Summer of GaN webinar, which is the next generation audio amplifiers with GaN EPC GaN FETs for compact and high fidelity. Before we get started, I'd like to go over just a few housekeeping items for today's event. You will have the opportunity to submit text questions to the panel by just simply typing your questions into the Q&A feature, bottom of the screen. You may also send in your questions at any time. We'll collect these and address them during the Q&A session at the end. So don't worry if we don't immediately answer your question. We'll get to it at the end there. Without further ado, I would like to introduce our speaker today, Tiziano Morganti. He is a senior field applications engineer for the EMEA region at EPC. Tiziano received his PhD in 2006 in electronic system design from the Università, excuse me, I don't pronounce this correct, Tiziano, my Italian's not the best. Università di Studi di Firenze. With over 20 years in the power electronics industry, Tiziano has held many roles as an electronics design engineer, electrical team leader engineer, system design engineer, and a GaN hemp-based inverter concept and design leader of a 2 kilowatt inverter. Tiziano, thank you for joining us today.
Thank you very much for the introduction, Will, and welcome to everyone. So let's go over the presentation. So we will talk about an introduction about the audio amplifier market, what are the main challenges, then brief introduction about Class-D amplifiers and what are the main requirements. We will introduce the use of EPC GaN FETs for Class-D audio, and mainly we will talk about the EPC9192 Class-D Audio Demo Board. So let's go over the market for audio amplifiers. So we have 3 main segments. One is the home or consumer segment. So mainly we have soundbars, hi-fi amplifiers, subwoofers, and so on. Then we have the pro audio market. We have rack mount amplifiers mainly. We have music instruments. We have active speakers for PA. And then we have let me move this. Then we have the transportation market. So mainly car audio, but also other vehicles like boats and AGVs and so on. So regarding how much gallium nitride has been used in each of those segments, we have growing adoption in home consumer applications, hi-fi and high-end amplifiers, and mainly for the higher fidelity and the compactness and low heat generation we can achieve. Also in the professional market, we have been used in multi-channel products, so where many channels need to be fit in a limited space. And of course, the main advantage is the low heat generation, so the ability to avoid the use of a fan or to be able to use a very slow and silent fan. In transportation, we have been adopted in aftermarket audio amplifiers. Okay. So what are the main challenges for an audio amplifier? In the low power segment, so we are talking about below 100 watt per channel and portable devices. So we need to guarantee as long as possible playtime for battery powered devices. And in home systems, we have a challenge of fitting as many channels as possible in a small system. So we have examples of multi-channel home cinema systems or sound bars that deliver a significant power, even low power per channel, but many channels in a small box. And in this segment, the consumer audio products are very price sensitive, so the design is often optimized to minimize the bill of material. And okay, let's go over the next step. So mid power, we are talking about power in the range of 200 to 500 watts per channel. In this case, as opposed to the low power segment where mainly integrated circuits are used, in this segment, the power or voltage level is not possible to manage with ICs, which are limited to about 40 volt. And also it starts to be challenging the heat sinking and the thermal management solution. In the high power segment, we are talking about power between 500 watts and few kilowatts per channel. The heat sinking is almost always mandatory, and it can take space and cost on the solution. And also the voltage level is requiring 150 or 200 volt devices. And one challenge here is not all the switches are suitable for the application. So very brief introduction about what is a Class-D amplifier. So Class-D amplifier is a switching amplifier. So we have an analog audio signal, and this is translated into a PWM modulated signal, which is amplified by digital power stage. And then we have a low pass filter that is reconstructing the analog audio from the PWM signal. So EPC is providing a solution for the power stage. So we have discrete components, and we have also power stages, so gate driver plus the power devices. So what are the main requirements for a Class-D audio amplifier? So first of all, the power output is the main, let's say, requirement that we have. So we specify the peak voltage, the peak current output, rated power, and we can discuss a few hours about what is the definition of rated power, but it's not a topic of this webinar. Then we need to achieve sufficient audio performance. So depending on the application, we can have different requirements from very easy to achieve to very challenging in terms of output noise, total harmonic distortion, intermodulation distortion, and the bandwidth needs to cover the 20 to 20 kilohertz audio bandwidth at least. Then the next requirement is how much heat generation, so how much losses can you afford. So basically, the first two requirements, so the power output and the audio performance, are not usually an issue in modern Class-D audio design. Heat generation is one of the differentiation factors, and you need to reduce both the idle losses, so the losses when you have very low power output or no signal output. So in this case, an audio amplifier is staying most of this time in this low output power state. And also, it is important to reduce as much as possible the losses while delivering the long-term power. So basically, those are defining are limited usually by the power dissipation. And if you can reduce the long-term power losses, you can also reduce the size and the cost of the heatsink. And also another requirement is the size, the total size of the solution in terms of the usage of PCB space and the height of the solution. So especially in high channel count designs, this is also an important factor to consider. So in terms of selection of the switches, how is made? So basically, we can define a sine wave rated power output, which is the square of this peak voltage divided by 2 times the load. And so once you know the output power and the rated load, you can derive what is the peak voltage, and this provides the VDS ratings for the power switches. So in a case of half bridge topology, the VDS ratings needs to be at least 2 times the peak voltage plus some margin. In case of full bridge topology, VDS ratings needs to be above the peak ratings plus some margin. In terms of examples, 100 watts on 8 ohm in an half bridge is requiring a 100 volt device. 450 watts on 4 ohm in half bridge topology needs a 150 volt device. 3000 watts on 4 ohm needs a full bridge topology with 200 volt device. And this is pretty much the highest power we can achieve on 4 ohm. In terms of output current, the peak current is computed as the peak voltage divided by the rated load plus some margin, because the load can go below the rated nominal impedance in some frequency bands or in some conditions. So from this, we can determine what is the RDS-on or the size of the device. Then we have other parameters to consider, the junction to case resistance for the thermal design, gate charge, output charge, reverse recovery, and so on. So it turns out that it's not easy to find a low RDS-on and above 100 volt VDS ratings switch, which is also which has also good parameters in terms of gate charge, output charge, reverse recovery. Especially silicon MOSFETs are lacking a very good body diode, and so it's not trivial to find to select the right switch for this application, unless you try our GaN FETs, which is basically a better switch because we have lower losses, so we can get lower RDS-on and much lower switching losses compared to silicon MOSFETs. So in this case, we can reduce the size or even eliminate the need for the heatsink. We can reduce the requirements on the ventilation, or even design a solution with no forced air cooling. Also, being a very lower switching losses, we can achieve higher switching frequency. So we can allow the use of smaller and less expensive inductors, and also make easier to implement feedback control loops with very good control over the whole audio bandwidth. And also, the open loop waveforms are much more ideal compared to silicon. So we can achieve very low propagation delays. We have a selection of gate drivers which have much smaller propagation delay jitter, and so we can guarantee a better open loop linearity to start with. So conclusion, we can say our devices can guarantee a future-proof product, and which is quiet and also wastes less energy. So in terms of comparison, very used silicon device compared to our GaN. So we can consider this 200 volt silicon MOSFET. It's you can see RDS-on in our EPC2215, which is widely used, or also the new QFN EPC2307, which turns out to be a very good device for Class-D audio. So you can see RDS-on is 3 times lower, gate charge is 6 times lower, and also we don't have reverse recovery, and the output capacitance is similar to the silicon device, and the size of the device is much smaller. Then how do we compare against silicon? So we have this table here. So we have different conditions, starting from the most challenging. So the peak power during the crest of the sine wave, then sine wave power, and then long-term power at 9 dB crest factor or 12 dB crest factor, and then the idle losses. So starting from the peak power, we have 30 amps peak with 70 volt peak output. So this is causing a lot of losses in the in this case in the high side device, because it has a large duty cycle, and it's also switching a large current. So we have conduction losses. We have a saving on the conduction losses, which is about 30 watts. we have a saving of about 10 watts in the switching losses. We do not have recovery losses, so this is another 40 watts saved. And also the gate drive losses are much smaller. So if we compare 90 watts on the silicon device against 13 watts on the EPC GaN FET, and concern that designers have, yes, our device is much smaller, so it's more difficult to dissipate the heat, but it's also true the heat generated is much smaller than in the silicon case. Then in the other cases, we have the same lower losses and mention to the idle losses in the silicon MOSFETs. It's the gate drive losses are not negligible, while in our devices we have about 10 times smaller gate drive losses. So you can save some power also in the gate drive circuit. Okay, let's start to talk about our EPC9192 demo board for Class-D audio. So what were our design goals? First of all, we wanted to provide a design suitable for the mid-power and high-power applications, so between 200 watts and 2 kilowatt. We wanted to show the compactness that can be achieved with our GaN and the high efficiency. So we try to optimize for low idle losses and also to get full load, high full load efficiency. And also in terms of the audio performance, our priorities were, first of all, low output noise, then low distortion, and last but not least, low output impedance. And also we wanted to provide a way to easily customize the solution. So use the demo board to build your own prototype and evaluate the GaN performance. So this is the demo board. We have a reusable motherboard, which has the connection to the power supply between plus minus 42. So it's a split power supply, so with ground, negative and positive rails. So from plus minus 42 to plus minus 85 volt. Then we have the housekeeping power supplies. The input here is regulated 12 volt. We have protection on the motherboards, so under voltage, over voltage, over temperature protection, and over current protection. And we have also the audio connectivity, so unbalanced inputs, balanced inputs, and the speaker outputs. Then we have a daughter board, two daughter boards, one per channel with the PWM modulator. So the design is switching at 600, about 600 kilohertz, is a self-oscillating design with feedback taken after the output filter. And then we have two daughter boards, one per channel with the power stage. So this is just implementing an half bridge with PWM input, enable input, and the half bridge plus gate driver, and the output filter with the inductor and the filter capacitor. So this is the power stage. We have our GaN FET. We are using EPC2307, which is a 10 milliohm max 200 volt QFN part. Is here in this picture. We are using an on-semi NCP 51820 gate driver, which is this one. We can provide PCB-only cooling at the rated power and output, and also voltage supply. Then we have a neat sink mounted on this power stage to being able to operate up to the maximum rated power. We can deliver about 80 volt peak, 30 amps peak, which means about 700 watts on 4 ohm or 370 watts on 8 ohm. Actually, we can do slightly above this. So talking about the power stage, we can describe what we did in the power stage in the schematic. So we have a PWM input and we have a level shift to the negative rail. With so this is the low frequency DC path, and we have an high frequency path with this 100 picofarad bypass capacitor. Then we drive the gate driver with two opposite signals, and the gate driver is implementing the dead time generation. Then we have the enable input with just the level shifter to the negative rail and the input of the gate driver. The gate driver, the high side is powered with a bootstrap power supply, and the good thing about this on-semi driver is the integrated low dropout regulator. So we have a 12-volt supply to the gate driver. The bootstrap voltage can be affected somehow by the widely variable duty cycle, but the integrated low dropout regulator is guaranteeing a 5.2 volt drive to the gate of the GaN FETs. Then we have the dead time setting resistor, which is the dead time is generated by the gate driver. We have provision for the Schottky diode in parallel to the GaN FETs, but we will see in the next slides it's better to do not use them. Then we have temperature sensor, which is coupled to the source of the low side FET, and this is implementing an over temperature protection. And also we have done some additional filtering. So we have the switching node, which is switching very fast. We have a small inductor with very high self-resonant frequency. We have a snubber to reduce the high frequency noise, and then this pre-filtered signal it's fed to the output inductor, which is an off-the-shelf 10 microhenry inductor, and this is removing some very high frequency component and reducing the radiated emission of the main inductor. So it's removing some requirement from the output filter design. In terms of the layout of the power stage, we used a 4-layer design with 2 ounce copper. Components are only on the top side. And those are the 2 GaN FETs. We are using vias in pad, and we could fit 48 vias in pad for each device. We are using middle high frequency capacitors. So those are 4 by 10 nanofarad capacitors in 0603 sides. And we are using the switching node polygon is buried in the inner layer. Those are the optional extra diodes. Those are the medium frequency bypass caps that are taking some of the ripple. Most of the ripple is managed by the electrolytic capacitors you see here on the sides. This is the gate driver. So this is the high side, and this is the low side gate driver sections. And this is the first inner layer. So you can see if we start from the, I think this, so this is the high side. So this is the positive rail on this side of the bypass capacitors. So you start from here, you go to the drain of the high side device, then you go to the source of the high side device, which is the switching node. So this polygon here is the switching node going to the inductors. Then this switching node is also connected to the drain of the low side device. And then from the source of the low side device, you get back to the negative rail and you close the power loop. So you can see the power loop is very compact and the parasitic inductance is very small. Also, is worth to mention the switching node is routed also below the high side section of the gate driver, and this is used as a return path for the gate drive signals. Same thing on the low side with the negative rail. Also, we have here the dead time setting resistor that can be modified to change the dead time. So a few words regarding the dead time. We did some experiments and so we could see a shorter dead time is causing extra idle losses because we start to lose full zero voltage switching in the output stage. So some of the energy in the output capacitance of the FET is converted into heat. So we could see every 5 nanoseconds shorter dead time with the used inductor. It means about 0.5 watts of extra idle losses at the maximum rates of plus minus 85 volts. Also, shorter dead time is reducing the losses in the freewheeling at high power. So every 5 nanoseconds shorter dead time, we could see about 5% lower losses at medium to high power. Also, shorter dead time is reducing THD, especially at the high frequency measurements at 6.66 kilohertz. Also, we are using a 50 nanosecond dead time, and this is dictated by the optimization for the lowest idle losses possible. And with this combination, we could get less than 10 watts of losses at plus minus 85 volt for both channels, including the motherboard losses. Of course, you can choose a different trade-off by modifying the dead time setting resistor. Yeah, losses are measured with Schottky diodes. Okay, this is a test we made. So we designed a custom inductor, which is 7 microhenry, and we were able to reduce the dead time with less burden on the idle losses. So we did a comparison between 7 microhenry inductor and the 30 nanosecond dead time against the standard 50 nanosecond dead time and 10 microhenry inductor. This test has been carried out at plus minus 85 volt and with 400. So the rated power at this voltage level is about 400 watts at 8 ohm. So what we could see is higher efficiency at medium to high output power. You can see we reached 96.6% efficiency at rated output power. You can see also from the losses, we have about 1 watt more of idle losses. So 5 watts against 4 watts. But you can see starting from about 10 watt output power and up, we can save a significant amount of losses. Especially at high power, we get a saving of about 3 watt in the losses. So this can make easier the thermal design of the heatsink. So in terms of the thermal solution we adopted in the power stage, one factor that is helping is the 2 ounce copper in the PCB. So it helps to spread the heat on the PCB. Also, the via-sink pad are transferring the heat vertically into the PCB layers. And so we have also additional vias here So we have this top copper layer, which is also connected to an identical layer on the bottom side. We have also used 1206 copper jumpers that are used for two reasons. One, to spread the heat on horizontally on the PCB, and this is a limited effect, and we decided to connect them on the drain pad here, because this is the widest area to bring out the heat from the device. And also they are transferring the heat vertically to the heatsink. So the heatsink is mounted on top of those corners here, and it's spring loaded, and it's held by those push pins on the PCB. This is the temperature sensor, and finally we have a thermal interface material which is very critical to the application. So we needed to select a very high thermal conductivity soft get pad, and this is also covering the copper jumpers to transfer the heat from the PCB to the heatsink. Okay, so we have a couple of cases here. One is with no heatsink and no fan, with plus minus 48 supply rails, 4 amps RMS output current, which is full sine wave power on 8 ohm, or it is 250 watt on 4 ohm with 9 dB crest factor. So we could see the temperature of the FETs is 78 degrees, PCB is 66 degrees, inductor 61, and ambient was 25 degrees. Then we have another case with the heatsink mounted and 200 linear feet per minute air cooling, and plus minus 82 volt supply rails. 10 amps RMS output current. So this means 350 watts on 8 ohm with sine wave power, or 700 watts on 4 ohm with 6 dB crest factor. And this is most likely a very dense signal. So it's even can be stated for very high power subwoofers, in example. So in this case, we have the heatsink at 71 degrees, the PCB is 61 degrees, the inductor is 56 degrees, and the ambient was 25 degrees. So the airflow blowing on the board is helping to keep both the PCB and the inductor cooler than the previous case. We have, so looking at this picture, the hottest part of the board was the PCB close to the Schottky diodes. So this is first, let's say, mention to the losses we can get on the Schottky diodes. So regarding the switching node waveform, this is an example at 20 amps output current. So this is the output current. You can see here the switching node at plus minus 82 volts of power supply. So you can see here the dead time so the rails is going slightly negative in the freewheel region of the both the Schottky diodes and the GaN FET. Then you can see how clean is the switching waveform. So thanks to the layout we implemented, we have virtually no overshoot. Then we have the high side turning off. This is going into freewheel. This is the dead time still, and then the low side is turning on. So if we look at the zoom version of the rising edge and falling edge, you can see this is the hard switching transition. So you can see here some hump in the waveform, so you can get some clue that something strange is happening here. So it looks like a reverse recovery of the Schottky diodes, while the falling edge is clean because it's just freewheeling, and So it's switching because of the current flow in the output inductor. So we did some experiment and we try to answer to this question: are Schottky diodes any good? No, that is our conclusion. So let's see why. So basically, we could see from the waveform some recovery, and then we had to use low-rated Schottky diodes, 200 volt. There is no good diode above 200 volts, no good Schottky diode above 200 volts. We had also to use a 1 amp rating for the diode because of the small size. So if you need to go to higher current rated diodes, they will be bigger than the GaN FETs. So this looks strange. So you have, this is the controlled switch, and this is the freewheeling diode. And also, anyway, we could see at 600 kilohertz, the recovery losses related to the diodes are way too much. So they are a very significant part of the losses. So, so if you consider silicon diodes rated 300 volts or above, you get this kind of recovery charge, tens of nanocoulombs. And if you consider Schottky diodes, they have some recovery time, so they most likely have some recovery losses associated with the guarding structure or the protection structure of the Schottky diode when you use them at very high currents. So we have a zero recovery device. We don't like to pair it with a diode that adds recovery losses. So in Italy, we say we cannot have a supercar with bicycle wheels. This is a joke we use in Italy a lot. So do we need to use extra diodes? Let's see what effect are they doing if we have them or we remove them. So first of all, we asked ourselves, what's the impact on the THD? So we measured the THD with and without diodes, and especially we wanted to look at the harmonics in various conditions of output current at 1 kilohertz and 6.67 kilohertz. And what we found is, yes, we have a small increase in the third, fifth, and seventh harmonic, but like from the orange here to the purple. So it's like very small, like less than 10%, 5%, something like that. So basically, we can say very small or negligible improvement by adding diodes to the half bridge. Then what is the impact of the diodes on losses? So we remove the diodes from one of the power stage and we run at the same current. So 5 amps output, 1 kilohertz plus minus 55 supply. So we run them for 5 minutes with no ventilation and heatsink mounted. So you can see the difference. So the power stage with the diodes ran pretty hot. So the heatsink was running at 105 degrees and the inductor was 64. Compared to the power stage without the diodes, you can see 82 degrees on the heatsink and 57 on the inductor. So it's more than 20 degrees difference, which means with diodes, adding diodes, we increase the losses by about 30%. So we don't really want the diodes to be there. Okay, so let's have a look now to the audio performance measurements on our kit. So this is the setup. We have 2 power supplies set at the same voltage. They can go from 42 to 85 volt DC. Then we have resistive load, can be 4 ohm, 8 ohm, or 2 ohm also. So we are just limited by the output current, not by the output impedance. It is often recommended to add a couple of big capacitors in parallel to the power supplies. We have seen during our measurements regulated power supplies going crazy because of the current ripple flowing when you run the amplifier at low frequencies, like 100 Hertz and below. So it's recommended to place a couple of 2,200 or 3,300 electrolytic capacitors on the power supply connectors. Then we used for our measurements the audio precision APX525, and we used balanced connections for both inputs and outputs, but also we measure the output directly at the connectors of the EPC9192 to remove the influence of the cabling. So I've seen often measurements taken directly from the load, but this is measuring not only the amplifier, but also the cables that you are using to connect to the load. So this is the introducing the least perturbation of them on the measurements. So it's a Kelvin connection to the instrument. Okay, so we could measure the frequency response, open load, 8 ohm load, 4 ohm load, and 2 ohm load. So you can see there is a very small variation of the frequency response with the load. This is a 0.2 dB scale per division. We have very small output impedance below 10 milliohm up to 5 kilohertz. It goes up to about 25 milliohm at 20 kilohertz. So basically, we have a flat response with which is load independent. This is the THD versus the output power on 4 ohm. It's measured at 100 Hertz, 1 kilohertz, and 6.67 kilohertz. So we have low THD up to full power. So this is THD versus frequency at 1 watt, 10 watt, and 100 watt on 4 ohm load. So we have low THD, which is increasing just a little at high frequency. This is the noise floor FFT at 32,000 samples, 48 kilohertz with the audio precision equiripple window with no signal input and 4 ohm load. So you can see pretty low noise on the output. And this equates to 38 microvolt A weighted. So we could achieve above 120 dB signal to noise ratio. This is the FFT with 1 watt at 1 kilohertz on 4 ohm load. It's 0.003% THD. Then this is intermodulation measurement FFT with 5 watt on 4 ohm load. It's the CCIF IMD is below 0.04%. So what we will do next? So we are working on optimization of efficiency. So we work on the removing of the Schottky diodes. We are investigating how to reduce the dead time, and most likely we need to get a better inductor with lower inductance, lower losses. Then we can optimize the noise. We have something to do on the input stage and also on the feedback loop. Then we can improve the THD by improving the amount of feedback we can provide with our controller. And then we have to optimize the layout to reduce the crosstalk between the two channels and be able to reduce the interference tones between one channel and the other. Okay, so summarizing, we are seeing adoption in the Class-D audio application of GaN, which is speeding up. So we have several customers working on a GaN solution. EPC has the widest offering in the 100 volt to 200 volt range, and we are seeing the EPC2307 is a very good solution for Class-D audio. But we have also in some lower power the chip scale parts in 100 volts, so EPC2204 and EPC2059. So we can enable a lower loss, higher power density, so smaller amplifier, which can be integrated into multi-channel products. And also the EPC9192 is a very good starting point for evaluation, and also by getting the design files to design the customer solution. And you can reach out to us to know more about EPC GaN for Class-D audio. Okay, then mention to the next webinars we will run. So August 7, we do a webinar about gate drivers, controllers, and PCB layout. And then August 21st, the web-based design tools we have available on our website to start the design with us. Okay, thank you very much. Now it's time to take your questions.
All right, thank you, Tiziano. Now we're going to begin answering the questions submitted during today's presentation. As a reminder, you could still submit the questions by typing your questions into the Q&A feature, which should be at the bottom of your screen. Tiziano, our first question here. Schottky diodes above 100 watt have PN junction paristic, hence a bit of QRR. Have you tried SiC diodes?
I have not tried them for one reason. They start to have forward voltage, which is around 1.5 to 2 volts, which is already removing the advantage you can get with them, because our GaN FETs has a freewheeling voltage of about 2 to 3 volts. And the purpose of the Schottky diodes was to have freewheeling voltage below 1 volt to both improve the THD and reduce the losses. So in my opinion, there is no point in trying silicon carbide diodes because they are expensive, they are big, and they will not provide many advantages. So the next step for us is to try to remove Schottky diodes, keep the dead time long for low power operation to optimize the idle losses, and reduce the dead time when the output current is high enough to optimize the losses at high power by reducing the freewheeling losses just by reducing the dead time. So we don't need any other switching device than our EPC FET. So that's already a good switching device. We don't want to compromise with adding other devices in parallel.
Okay, thank you. Next one we have here. Why have you closed the feedback loop after the filter?
Okay, that's a good question. One reason to do that is achieve a better control of the output of the amplifier. I mentioned we have, can also bring up the slide. this one. I mentioned I have a very small output impedance up to 20 kilohertz, and this is guaranteeing the least noise coupled to one channel from other switching devices on the system. So you might have basically a couple of things going on. One is in a multi-channel solution, you might have one channel that is coupling its switching noise to the other channel. Or you can also have the power supply, the switching power supply that is coupling to the output of the amplifier. So you don't want to have coupling to the output. And one way to reduce this coupling is reduce the output impedance up to 20 kilohertz. And this can be achieved only by closing the feedback after the filter. The second reason to do so is for the same reason, you become more independent from the linearity of the output filter, so you can get some correction of the distortion induced by the output filter, and so you can get, in general, a better audio performance in terms of THD and noise. And of course, not all the amplifiers or solution can be implemented by this kind of feedback, but it's we believe it is one of the best solutions you can adopt.
Fantastic, thank you. The next one here. Have you investigated current FB from example from output to input?
Sorry, current
FB?
Current feedback.
Current feedback.
Well, we have that one going on with this kind of feedback, actually, but it's not direct current measurement, it's indirect current measurement. So we estimate the current ripple in the inductor by derivative of the output voltage. So the derivative of the output voltage, so you have the ripple voltage in the output capacitor. If you do a derivative with a capacitor so an high pass filter with very high corner frequency, you get an estimate of the ripple current in the capacitor, which is in turn the ripple current in the inductor. So this kind of feedback is using this to close a first inner loop. Then we have another voltage loop that is using the output voltage and is operating mostly in the audio bandwidth. But we didn't try with measuring directly the current from the inductor and using it to close the feedback. So this is, I hope this is answering to the question.
Okay, moving along here, the next one. EPC used to have a single chip with 2 symmetric GaN FET 100 volt. Why not using that to further optimize the layout?
Yeah, first of all, we wanted to go above 100 volt ratings with our devices. So we ruled out the use of the power stage because it's limited to 100 volt. Of course, it can be used and it will provide a very compact solution. Currently, we have a limitation on the maximum on time, which is also stated on the datasheet. It cannot stay on for more than 200 microseconds. But we are working on it. Maybe in the future we will have a solution which removes this limitation. But okay. So the short answer is we needed the 200 volt device.
All right. The next one we have here. What considerations were made for MLC capacitor DC bias capacitance value change?
Yeah, that is a good one. Actually, it's one of the things we need to improve to increase our efficiency, because we now have the high frequency capacitors are 10 nanofarad or 603. They might drop to maybe 3 nanofarad each at high voltage. But they are 4, so we have 12 nanofarad that is just dealing with the switching transient. So it's enough capacitance because the switching transient is lasting nanoseconds. Then we have, let me show you the slide with the layout, this one, okay. So then we have those mid-frequency capacitors. So we have 100 nanofarad, 200 volt between the plus and minus VCC. And we have a 1 microfarad, 100 volt from ground to the rail. And those are dropping significantly. Maybe we have an effective, an actual 300-400 nanofarad capacitance between rail and ground. And if you consider we are switching at 600 kilohertz, the impedance of this capacitance is in the order of maybe a few hundred milliohms. So most of the ripple is going to the electrolytic capacitors. So those two electrolytic capacitors are taking most of the ripple, and we estimated they have a not negligible loss. So they might dissipate a few hundred milliwatts each. And this loss, we need to get rid of it to increase the efficiency. So having to redesign this, of course, we remove the diodes. I would just put more capacitors, so duplicate those 3 instead of the diodes. And I would also either increase the number of those capacitors, the electrolytic ones, or select carefully lower ESR ones, because we use the capacitor that is about 100 milliohm ESR, might get maybe 50 milliohm at higher temperature. But still, it's a significant resistance that we want to get rid of to reduce the losses. So yes, it's a good question. So next time, double the ceramic capacitors and double the electrolytic capacitors.
Okay. Moving along here, have you listened your demo board in an A/B comparison with other amps?
We did it. I didn't personally do that, but it's the feedback we had. It's good, meaning that first comment was it is very, very quiet. So the output noise is very, very low. And also it's very clean. So we had positive feedbacks about comparison with other amplifiers.
Okay. And the last one here, are you looking at dynamically adjusted dead time?
Yes, this is the next step. So it would be actually it's going to be not super difficult to do, because I need to try it. But now the dead time is set with this resistor to 50 nanoseconds. Then what we have now is the 2 PWM signals for the low side and high side are going straight. Yeah, we have this low pass filter here to the inputs of the gate driver. So what we can do is implement 10 to 15 nanosecond dead time using those filters. So it's just adding a diode here on the discharging path and here. And then we need to bring an additional signal to short the dead time input of the gate driver to ground, because this gate driver, when you pull down this dead time setting pin below 0.5 volt, it's entering a mode that is using the external set dead time. So this is pretty easy to do. It's few components added, and I believe it will provide big improvement in terms of efficiency and also in terms of THD at higher power.
All right. Well, thank you, Tiziano, and everyone for attending today's webinar. If we did not have a chance to answer your question, we'll reach out to you with a response. Likewise, if there are any additional questions, you can always email us at info@epc-co.com. Again, that's info@epc-co.com. You'll receive a follow-up email within 24 to 48 hours with also a link to view today's recording of this webinar. Lastly, the next installment, as Tiziano mentioned, of the Summer of GaN is going to be scheduled for August 7th. And we're going to be talking about the GaN First Time Right, which covers controllers, gate drivers, PCB layout tips for DC to converters. In this comprehensive session, we'll guide you through some of the basic design process to ensure your GaN-based projects are executed flawlessly from the start. We will also cover gate drive techniques made for GaN controllers and learn PCB layout optimization tips tailored specifically for GaN FETs and ICs in converters and motor drives. This webinar is great whether you're new to GaN or looking to refine your design. Registration link is available on our website at epc-co.com. Again, epc-co.com. And thank you for joining us today, and we hope you have a great rest of your day wherever you may be.
Thank you. Have a good day.
Thank you, everyone. Take care.